All right, for example 4, it says Avery puts up a radio antenna tower in his yard. Here's his tower here. Ella tells him that their city has a law limiting towers to 50 feet in height. How can Avery use the lengths of his shadow and the shadow of the tower to show that his tower is within the limit without directly measuring? So basically, you put it up. Tower's up. And then, after he gets it up, Ella says, hey, there's a law that says it can't be 50 feet high. Typical, right, that you find out after the fact. So anyway, what we're looking at here is Avery creates a shadow, so does the tower. And within the same general area, people's shadows and building shadows and everything, they have the same angle to the sun at any given point in the day. So there's an assumption here that these angles are congruent, but it's a pretty good assumption. So if he's standing that close to his the tower, the sun's making pretty much the same angle for both, or close enough that we can assume them to be equal. He has the capacity to know how tall he is, and he can measure his own shadow, right? So he has the ability to do that. He could also measure the shadow of the tower. He doesn't know the height of the tower, though. So that's kind of what we're looking at here. So if I just call the height of his tower X, just to give it a name, so I don't have to use ST. I want to demonstrate, first off, that we have similar triangles here. You can see that Avery is standing straight up, making a right angle with the ground. And this is making a right angle with the ground. This angle is congruent to this angle. So looking at the two triangles, we have angle-angle congruence. We could also have side-angle-side, or congruence, similarity. Angle-angle similarity. We might want to try side-angle-side, but we don't know that side yet, so we couldn't use the side-angle-side, right? So what we have is angle-angle congruence. He stands perfectly straight up. You know, if he's leaning one way or the other, then it's not going to count. So he's perfectly straight up. We'll assume he got his tower perfectly straight up too. He's using tools and stuff to make sure it's going straight up. It's not leaning. A leaning tower of whatever that is. So angle-angle similarity happens here, which means that triangle ABC is similar to triangle RST. And Avery's segment, his height 6 feet, is proportional then to ST, the tower's height. And AC, his shadow, is corresponding to the tower shadow. So we can just set up a proportion here that if we put Avery's shadow over the tower's shadow, should equal Avery's height over the tower's height. Demonstrate similarity of triangles, use that fact to create some sort of proportion that can be solved to figure out a missing piece. Okay, I can cross multiply immediately. I could also reduce the fraction if I felt like that's 1/8. Doesn't matter. I'm going to just go ahead and cross multiply immediately though. So typically that's what people do. So 5 times x is 5x. 40 times 6 is 240. We divide both sides by 5, and we get x equals 48 feet. So, how can Avery use the lengths of his shadow and the shadow? So the question saying, how can we do this? Well, set up a proportion, show the triangles are similar, set up a proportion, and cross multiply. But the actual height of the tower is 48 feet, so Avery could say back to Ella, well, it's 48 feet high, so it's within the limits of the law because it has to be less than 50. So Avery's in good shape here for this one. Again, that's one of the more common ways that similar triangles are used out in the real world. A lot of times you want to know how tall something is without climbing up to the top and dropping a tape measure, right? So it's easier to measure along the ground than it is to measure up and down. So it's a pretty effective way of measuring tall objects.